All right. Day 2. Quick warm-up. So here's the die. It has 1 1, 2 2s, 2 3s, and a 4. So the possible numbers are 1, 2, and 4. Again, you do not have to write out each occurrence, just what are the possibilities. Is it uniform? No. Now, what's the probability of a 1? Well, there's only one of those. So that is 1 out of 6. That's unlikely. A 2. Again, there's 2 of those. So that's 2 out of 6. Still unlikely. Less than half. 2 out of 6 on the 3s. Okay. 4, there's 1 out of 6. And 6, there's none. Now notice, 1, 2, 3, 4, 5, 6. Okay? Those add up to 6 right there. So, unlikely, unlikely, but impossible there. There is nothing that has at least a 3 out of 6 a 50-50 shot. Okay, a bag contains 1 red, green, 5 green, and 4 yellow. Okay, so first off, it's always good to find out how many there are total. That's 10 total. It's always good to make a note of that. Okay, now, what's my sample space? I have red, green, and yellow. That looks like a 4. I'm just going to erase that. Now, is this probability uniform? It is certainly not, because there's more greens than reds and yellows. And there's more yellows than reds. So, probability is green 5 out of 10, which is 1/2. So that would be equally likely. It doesn't ask us that, but I think it does below, doesn't it? Nope, it doesn't. Okay, so equally likely. Yellow, 4 out of 10. Well, that's a little less than half, so that's unlikely. Blue, there's no blue. So that's 0 out of 10. That's impossible. And a colored marble. Well, they're all colors. So 10 out of 10, that's certain. All right, new stuff. Day 2. Today we're going to talk about situations where 2 or more events are occurring. The sample space may get a little complicated, so we have other methods of stating them instead of just listing the outcomes. So, for example, we flip a coin 2 times. What's the sample space? Well, it's still just heads or tails. Those are horrible abrasions. But let's draw a tree diagram to find the sample space. So we start off with our first flip. We can get heads or tails. But then on our second flip, we can get heads or tails again, heads or tails again. So the true sample space of what could actually happen is we could get heads and heads again, heads followed by tails, tails followed by heads, and these are not the same. Even though it's one of each, it's different. Order matters. And then tails followed by tails. So there's actually 4 different outcomes in this case. Not 3. Heads, tails is different than tails, heads. All right. Rolling a die. So if you roll a die, there's different outcomes. So we can organize it like this. And let's think about it this way. It's not done this way here, but let's imagine this was a red die and a green die. Okay? Because it matters. So 1 and a 2 is different than a 2 and a 1. Because a 1 red, 2 green is different than a 1 green, 2 red. So here we have 1, 1, 1, 2, and so forth. And then we have 2, then 1, 2, 2, and so forth. I'm just going to hit pause, and that's what it would look like after it's filled out. So the reason I say the colors is it matters. It's different if you roll a 4 on one and a 5 on the other than a 5 on one and a 4 on the other. It makes a difference. So how many different possibilities are there? Well, there's 36 possibilities. 6 times 6. Okay? 6 red, 6 green. There's 36 possibilities. Now, draw a tree diagram and determine the sample space for selecting 2 scoops of ice cream where the choices are vanilla, chocolate, and strawberry. So, you're going to have your 1 scoop and then your 2nd scoop. So first off, you have 3 choices. Vanilla, chocolate, strawberry. And then on your 2nd scoop, you have vanilla, chocolate, strawberry. And this is why tree diagrams are a pain, because it gets really messy trying to do the same thing. So, my sample space, what combinations do I have? I could have vanilla, 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 chocolate, vanilla, strawberry. I could have chocolate, then vanilla, chocolate, chocolate, or chocolate, strawberry. And then I could have strawberry, vanilla, strawberry chocolate, and strawberry strawberry. Now you may say that's the same thing, you know, vanilla strawberry and strawberry vanilla, but it's not. Because if you picture in your head, you have vanilla on top of strawberry, or strawberry on top of vanilla. So, how many possibilities are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 different possibilities. Now, the fundamental counting principle. When a series of events are occurring, you can find out the number of possible outcomes by just multiplying the number of ways each event can occur. So, when you're doing something like this, flipping a coin 4 times, you could make a tree diagram, but it would get pretty hectic pretty quickly. So when you're flipping a coin 4 times, I'd like to do the dash method. Here's how many times you're flipping the coin. Each time, how many choices do you have? And then you just straight multiply. So it's 2 times 2 times 2 times 2, which is 16 possible ways. Rolling a 6-sided die 3 times. Well, you have 6 possibilities here, 6 here, and 6 here. That's 216 possible ways. Now, this comes in with security codes all the time. You have an iPad. There's a 4-digit password. How many possible passwords are there? Well, there's 10 digits, 0 through 9. And if there's 10 for each slot, that's actually 1,000 different codes, if you can repeat the numbers. How about this? Jeff has t-shirts, pants, and shoes. He has 5 t-shirts, 3 pants, and 4 shoes. If you just multiply those, 5 times 3 is 15, times 4 is 60. 60 different outfits, as long as he doesn't care how he looks, because some colors might clash. That's it.